big rise, like the output due to a step function in the input, until roughly t seconds later. So even though it's no longer a step, the information that I have step on the input comes out of the CSTR to a significant extent, big T seconds later. And that's what this is saying. This is saying, to a very dumb approximation, remember, when the time is not too short, so I'm not looking over here. I'm looking over here at a time on the order of t, or a little bigger than t. The information got delayed big T seconds in each CSTR. So the overall delay of the information getting from the beginning of my chain of non-interacting systems to the end of my chain of non-interacting systems is the sum of the delays due to the plug flow reactors with no reaction, plus the sum of the delays of the information getting through the CSTRs. And that's what this means. Is that clear? Are there any questions on that? Questions? Question. You look. The look in your eyes is saying, you want me to explain something, but I don't know. It's not telling me anything more specific. Am I reading your eyes right? No. Yeah. Okay. No. I'm saying if you have a question, just ask. I'm looking to see if anyone else looks like they have a question and they're afraid to ask. Don't be afraid. I don't bite. Okay. Again, you can interrupt me at any time. I don't mind being interrupted. All right. So again, we've been looking at systems in series where they were first non-interacting, and then here we need interacting systems. Now we'd like to look at systems in parallel. So let's look at systems in parallel. So let's look at the following system. Do I have that notation correct? I checked, just call it, I don't need a 3. So let's just call this x1 prime tilde, x2 prime tilde, y1 prime tilde, and y2 prime. And I'm going to assume that g1 and g2 are just a, b, 1 or 2, over 1 plus s, t1 or t. They're just first order systems. Now, from block diagrams, I'm going to need your help here. Remember, if I want to get y prime tilde in terms of x prime tilde, so y prime tilde, we always start from the right side and then work backwards. When I say right, I mean the heads of the arrows, not the tails of the arrows. Because I could have written the other, the mirror image of that. I start from the heads of the arrows to the tails. So why don't someone help me? What happens when I have y1 and y2 combining to give me y? What is y prime equal to in terms of y1 and y2 prime tildes? Let's have a volunteer. Remember, you looked at your nose from the last class before coming to this class.
Is it the sum? Is it the sum?
Just the sum. So this is y1 prime tilde plus y2 prime tilde. Now, what is y1 prime tilde in terms of g1 and x1 prime tilde? Somebody else?
Product? Is it the product
Of
x1 prime and g1 prime?
Yes. So this is just g1 prime tilde x1 prime tilde plus same thing down here, g2 prime tilde. Actually, I have two primes under g. g2 tilde x2 prime tilde. And what do I know of this split from x goes to x1 and x2? Somebody else? They're equal. So this is just equal to g1 tilde plus g2 tilde minus x prime tilde. Okay, so let's figure out what, this is my overall g. And let's figure out what my overall g is. So g tilde is equal to kp1 over 1 plus st1 plus kp2 over 1 plus st2. And I can put that under one denominator. And this is going to be kp1 under 1 plus st2 plus kp2 under 1 plus st1. And let's rearrange that numerator. So the numerator, so this is equal to g tilde, is equal to kp1 plus kp2. Let's rewrite the denominator. 1 plus st1, 1 plus st2. So it's kp1 plus kp2 plus kp1 plus s times kp1 t2 plus kp2 t1. I just multiplied it out. And just for fun, I'm going to multiply and divide by kp1 plus kp2. Just for fun. Now, what I'm going to do is I'm going to call this thing, let's let kp equal kp1 plus kp2. And let's let t3 equal to kp1 t2 plus kp2 t1 over kp1 plus kp2. Now, let's just think for a second of units. kp1 plus kp2 all have the same units, otherwise I couldn't add them. They have to have the same units. And remember, kp has units of y prime over units of x prime. So the units of y prime. And they all have the same units. Since the kp's have the same units, and t has units of time, so I have time times these two have the same units. So if both terms have the same units, it's the units of kp times time, and the denominator is the units of kp. So this has units of time. So that's why t3, I call it t3, because it has units of time. So therefore, this thing, g tilde, now becomes kp times 1 plus st3 over 1 plus st1, 1 plus st2. And let's notice something. The steady-state gain can be positive or negative. Because for example, let's say I have a CSTR. And I have, say, a reaction going on. A goes to products. If I increase the concentration of A, then the rate of eating up A is going to go down. So I increase the input concentration of A, and the rate of eating up A goes down. So I could have KP being either positive, these guys can be either positive or negative. No. KP1, KP2 can be of either side. Well, if they can be of either side, then T3 can be of either side. Because let's say KP1 is negative, and T2 is big. So in the numerator, this is big and negative and bigger than this. But in the denominator, KP2 might be bigger than KP1. So T3 can be of either side. And let's see what that means. Well, another thing I want to note before we go any further is, Red, can you take out your tables, please? Again, I don't remember which version you have. There are two versions. I have both versions, so let me get out my second version. Do you have the one that says page 110 on the top? I have both.
Oh, no, just so you see what we have.
Oh, is it the one that says page 110 or page 100?
110.
Okay, so if we look at the one that you all have, the one that says page 110 on the top. If you look at lines 5, 7, 8, 9, 10, look at those lines 5, 7, 8, 9, 10. And if you look, you notice in the numerator there's a 1 plus AS over, some denominator, polynomial denominator. And everyone has their, you should bring yours to class, that's why I photocopied it. Yeah, when it's this small, you're not going to be able to read it. It's a piece of paper. It's not that heavy. I think you look strong. You can carry it. Okay. So, people asked me during the semester, they said, gee, we always said A equal to 0. We always have a numerator that was just a constant. Well, that was only when we had things in series. Notice here in parallel, I have something that has a 1 plus ST3 in the numerator. So that in particular is we're looking at something like line 10. So if I have a step input, I'll have a 1 over S times this. So if I have a step input, so x prime tilde is equal to delta x over s. Then y prime tilde is g tilde x prime tilde is equal to kp 1 plus st3 over s 1 plus st1 1 plus st2. And the inverse of that, that's exactly line 10. So the inverse, line 10, is y prime of k is equal to kp, that comes along for the ride. If you're having trouble seeing this part of the blackboard, there are all these seats that are empty over here where you won't see any glare. If you're interested in seeing it. If you're not, stay where you are. And let's see what I get here. Here I get 1. And then I have plus 1 over tau 2 minus tau 1. So what's that 2 and what's tau 1? It doesn't really matter. 1 over t2 minus t1. t2 minus t1. And here I have t1 minus a, t1 minus t3. And here I have t2 minus t3. So there's my inverse. And notice that now the T3 contributes. And notice I have this 1 here. The 1, remember, T goes up and I lost something. This should have been e to the minus t over t1. And here I have e to the minus t over t2. Make sure I got that right. t1 first. Yes, t1. Okay. So let's notice as time goes to infinity, both of these exponentials decay to 0, and I'm left with the 1, and the 1 came from the 1 over s, just as we said before. The 1 came from the 1 over s, because that had a root 0. 1 over s is infinity when s is 0. And e to the 0t gives me a 1. Okay, well, let's notice here that I've got some issues. We have issues here. One of the issues is, first, I've got something added and something subtracted. And I also have different time constants. This isn't just such a simple case. I'm taking differences of time constants. And t3 could be positive or negative. So let's see what that actually means. So let's do a plot. And this is time. And here I can have y prime. And here I can have the initial value, y prime, for t less than 0. And, well, why don't we make it y prime for t less than 0? Or y of t less than 0. And I just want to make my picture consistent with, so we're going to make it. So what we would expect, remember this is often, and let's say this is y as t goes to infinity. What we sometimes would hope for is somehow I would get a monotonic rise. Now, of course, this is going to depend on what t1 and t2 are. But I can also get sometimes something that looks like this. And this is called overshoot. And this depends on the values of t1, t2, and t3. But what does overshoot mean? Overshoot means I have two processes, a fast one and a slow one. So in this case, to get overshoot, I've got a fast process and a slow process. And the fast process has kp greater than 0, and the slow process has kp less than 0. So what happens? The exponential of the fast process decays before this guy has moved very much. So this goes up, and it goes all the way up to where it would be with the kp greater than 0. Once this one has steadied, then the other exponential drops in, and it starts to decay. Now, I can also get something that, and there's a name for this, which I forgot. The name. This is called inverse beam. And here, we typically have T3 positive. I can also get something that looks like this. This is called inverse wave. And this happens typically when T3 is less than 0. And what's going on here? Here I have a fast process that has kp negative, followed by a slow process with kp positive. So initially, before the slow process kicks in, the fast process has lowered the value of y. And then the slow process comes in and raises it again. Now, how do I know that T3 is positive or negative in these cases? Let's look at T3. If I have a fast process, that means the t is small. And if I have a slow process, that means the t is big. So let's look at this. Let's say the first one is fast. So in this case, the first one is fast. T1, T2, 1, 2. here I've got T1 is small, T2 is big. 1, 2. And let's see how that tells me the sign of T3. Well, let's look. If, in this case, T2 is big and KP1 is big. T2 is big and KP1 is positive. This is big and this is positive. This is little and this is negative. So obviously this guy wins. So therefore, T3 is positive. What about here? In inverse behavior, T2 is big and KP1 is negative. T2 is big, KP1 is negative. If T2 is big and KP1 is negative, T1 is small, and this is positive, this guy wins. So it becomes negative. And just because it wins in the numerator doesn't mean it wins in the denominator. The reason it wins in the numerator is because T2 is much bigger than T1. You get rid of the T's, and the denominator can still be positive. So that's how I get this inverse behavior, or the overshoot, and that's why I have T3 negative here and T3 positive here. Any questions on that? And let's just notice that that's very hard to predict, that situation. That's not an easy situation to deal with, because when you need to be able to estimate how much of an overshoot you have and how much of an inverse behavior you have. And so those are more complicated. And when I say more complicated, that means we need to, when we have parallel structures, or if you like, when we have A not equal to 0, when we have when we have polynomials in the numerator that are not constant, then the situation is quite different. If you remember, earlier on we said if we're only interested in t goes to infinity in long term, where the stability is a long-term problem. Long term. If we're only interested in long term, I only need to worry about the denominator of y prime, because that gives me the stability. However, if I have a and the numerator, so notice it's the roots of the denominator that give me the exponentials. The numerator does not enter into the exponentials. However, the numerator enters into the coefficients. And sometimes those coefficients could be really important, because even though at long times this is stable and it goes to y prime, the coefficients can give me overshoot or inverse behavior. Now, let's say I'm dealing with pressure. If the overshoot, so the steady state pressure may be fine, but the overshoot could be enough to blow the reactor up. That's not good. I never get to the steady state because the reactor blew up. So, in that case, I need to look at the entire dynamics to get the maximum overshoot and maximum inverse when I have something in the numerator that's a polynomial. Are there any questions on that? What does T3 mean physically? Right now, T3 is just something that has time units. And it's not a real time because it can be positive or negative. It's just a combination that comes in to this equation. But it's not a real time because it can be a negative. So it's hard to ascribe to it a physical meaning as you just suggested. And that's why I didn't say it. But what it does is it comes into these coefficients. And it can change the sign of the coefficients. If T3 is positive at large, we can make this coefficient negative. If T3 is small or negative, it makes the coefficient positive. So it flips the sign of this, and similarly here. And that's how you get overshoot and inverse behavior. But it has units of time, but it's not here, I can't just draw on the figure what T3 is, whereas I can easily draw on the figure what T1 is. What I can't do is T3 because T3 is not entering into the exponent. When it enters into something that has time dependence, I can tell you what it's doing. T1 is giving me the decay time of this exponential. T2 is giving me the decay time of this exponential. But T3 isn't a coefficient, it's just giving me the magnitude. So, and it's not sitting by itself. It's T1 minus T3 over T2 minus T1. It's stretching this or flipping over. I'm sorry I don't have a better answer to that.
So essentially, we have to go into the Laplace space, right? To be able to do the calculations, get everything in the right form. Then we use the sort of the table to go back to reality, right?
Well, we don't have to go to the Laplace space. We could do this stuff before exam 1, where we do everything in the time domain. It's just easier to do it in the Laplace space.
But that's basically what we're doing. Like we're doing most of the calculations and rearrangements in like the complex plane. Oh, we're doing all the rearrangements, everything in the
We've done it because the algebra is much easier in the complex space. But the take-home message of this is when the numerator is not a constant, and we're worried about overshooting or inverse behavior, because if it's the pressure, we don't want to blow the reactor up before we reach a steady state. Then we need to go back to the time limit.
Okay.
That's exactly what we're saying. But working in the complex space is working in S space is the method. It's not the result. It's the method. I could have done the whole problem Pythagoras doing this, and I would have gotten this correct if I would have used it. But it would have taken me much more writing.